Okay, cool. So we appear to be live. So we are now in lecture 17 and finally coming to what I think is the highlight of part 2. So which is towards factorization of integer polynomials, which I presume is something that when you're thinking of polynomial factorization, you're probably thinking of this and not over finite fields or something of that sort. But I mean, the reason I really like this is because it puts together so many new ideas that you have learned over the last few lectures. And in order to make the final jump, we will need one extra idea, which is this notion of lattices, which on the face of it appears to be something completely unrelated, but we will see that this naturally will show up once we set up the problem the right way. I mean, so today's lecture is primarily going to be I'm going to spend a fair amount of time doing a recap of what we have done with respect to bivariate factorization, at least the key concepts, because the factorization over integer polynomials is going to mirror bivariate factorization a lot. And it's just that there are some particular situations where we might have to come up with a slightly different way of doing what we wanted to do. But morally, we are trying to do the same thing. So it will still involve, you start with some base case, you keep lifting until a certain point, and then you try to solve a certain system. And from that system, you will be able to recover a solution. So this is the general structure of the entire thing. But it'll be good to have a high level picture of what is going on, because then we can precisely say what is the change we need to make in order to do factorization for integer polynomials. And once we phrase the problem, we will sort of see that, okay, this problem has a slightly different nature, and that's where lattices will come in. But I will assume one theorem about lattices and finish the proof today. And in the next lecture, we will complete the proof of that one result we used about lattices. Okay, so let me just get to a recap, and this is because there's a lot of things that ended up getting used until now. So we began with some understanding of what finite fields are, some basic properties of finite fields. And one of the crucial things that we just ended up using so often initially was the fact that x power q power r minus x has a really useful factorization, in the sense that it just factors into the set of all irreducible polynomials of a certain degree. That is, whenever this degree divides r. Okay, and this is a very useful thing because in some sense, you're trying to figure out which of the irreducible polynomials divide my polynomial. And here is a polynomial that contains all irreducible polynomial. And then there's a question of filtering out what you need. And the GCD is perfectly suited for it. So that was one of the reasons why that was so useful. And we then took it up a notch and started looking at univariate polynomial factorization, where the one extra idea that came in there was the use of the Chinese remainder theorem. Okay, so if you want to think about the univariate factorization in one line, it's just this line that you're computing the GCD of h bar q bar k minus 1 over 2 with f, where h is something that you're picking at random. And we basically argued that with very high probability, this h bar q bar k minus 1 over 2 will have a non-trivial factor with f, if f was like reducible to begin with. Of course, what exactly this k was, it came from distinct degree factorization, etc., etc. But to me, those are like some extra details. The key idea is the fact that h bar q bar k minus 1 by 2, when you look at it in the Chinese remainder representation, roughly half of the coordinates will be +1 and -1. So therefore, when you add 1 to it, you will have a lot of zeros and a lot of non-zeros. And that's precisely what you want. Okay, so that was the one-line description of the Cantor-Sassenhaus algorithm. Okay, and then we decided to sort of say, okay, now that we know how to do univariate factorization, let's take it up a notch and try to do bivariate factorization, etc., etc. And there were times when it is useful to pretend as if we are working in the univariate world, where, let's say, if you're dealing with a bivariate polynomial, you can think of it as a univariate polynomial where the coefficients are univariate polynomials in y, maybe in the other variable or something. Okay, and Gauss's lemma is a way of somehow saying that if you decide to make this jump, where instead of thinking of the coefficients as being in the ring of polynomials Ry, If you want to think of it as fractions, like, rational functions or something, factorization patterns don't change. Okay. So one specific way to describe Gauss's lemma is that if somebody gave you an integer polynomial and a rational factorization gx times hx, then Gauss's lemma basically says this is a poor excuse for a rational factorization, because basically you can multiply it by a scalar. I mean, multiply and divide by a scalar such that both of them become integer factors. I mean, Gauss's lemma is a way of saying that there is no real rational factorization for an integer polynomial. They're basically the usual integer factorization, which are somehow masquerading to be rational polynomials by, unnecessarily multiplying and dividing by something. Okay, that's one way to interpret Gauss's lemma. And Gauss's lemma was very useful because we could then move to this notion of what is called a resultant. And this is an extremely powerful idea. And we've already seen multiple applications of the resultant. So a resultant is it comes from the Euclidean GCD algorithm in some sense, because you're trying to write a linear map compared to, with respect to the two polynomials. But if you want to zoom out and just say, what is a resultant? A resultant is a polynomial expression on the coefficients of the polynomials involved. That is, if you're thinking of the resultant of f and g, it's some expression involving the coefficients of f and g, such that this expression is zero if and only if f and g have a non-trivial factor. Okay, so it's a rather powerful, somehow it feels like I don't know, it's a little unclear that, the existence of a GCD can somehow be captured by an expression of this sort, but somehow the resultant happens to do that. Okay. And the resultant has several other nice properties which end up getting used multiple times. So firstly, one can think of the resultant as a way of eliminating variable x. So in the sense that it happens to be in the ideal of f and g. By that, what we mean is this can always be written as some a times f plus b times g, where a and b are both polynomials. In the sense that a and b are both in the same world that f and g are. Okay. So, and it's a little unusual in the sense that this appears to be an expression which again spits out a polynomial. But notice that this is actually just a polynomial in the coefficients involved. So even though an expression here looks like it is something that involves both x and y, somehow the left-hand side is actually just a polynomial in y alone. In some sense, you manage to eliminate x from this thing. And something that will turn out to be very useful is the fact that if you know that f and g are polynomials of degree at most d, one crude bound on what is the degree of the resultant is going to be something like 2d squared. Okay. And this was a main property that we ended up using, which is that a resultant is going to be zero if and only if the two polynomials share a non-trivial GCD, where non-trivial is suitably defined in terms of which variable it's a resultant. Okay, so this is again a recap of what the resultant is supposed to be and what exactly the resultant captures. And now let's move on to the polynomial factorization algorithm in a high level. Okay, so I'm going to write it as a polynomial factorization algorithm for general polynomials. But we began by making a bunch of pre-processing assumptions. We basically said, without loss of generality, I'm going to assume that my polynomial f is nice. What does nice mean? Nice was something that satisfied three properties. So firstly, I want to make sure that f is monic in x. And secondly, I want to make sure that f is square free. And then the last thing was, I want to make sure that f of x comma 0 is also square free. Okay. And these are all things that you can do by some slight massaging of the polynomial. Like if somebody gives you a polynomial that is not nice, there is a standard way in which you can convert it to a different polynomial, some f tilde, factorize f tilde instead. And from the factors of f tilde, somehow recover the factors of f, somehow undo this thing. In terms of, I don't know, code writing, you can think of it as you write an adapter that converts an arbitrary polynomial into a nice polynomial, such that given the factorization of a nice polynomial, you can get back the factorization of the arbitrary polynomial. Okay, and this was roughly what it was. If f was not monic, then there was a way to renormalize x so that it now becomes monic. And if f was not square free, I mean, like you just take the GCD with respect to its derivative and you're done. And of course, when the GCD was all, if the derivative was identically 0, then you know your polynomial has a certain structure. So you've already simplified your polynomial, then you make use of that, etc. And with this thing was the place where the resultant ended up getting used for the first time, which is that you basically need to find a point alpha that does not kill the resultant. Because a polynomial that is square free such that this is not square free only means that y equal to 0 somehow satisfies the resultant. It kills the resultant. So since the resultant is a low degree polynomial, okay, fine. It may not be true for 0, but it will be true for some alpha. Okay, where, if your field is large enough for something, then you can pretend to shift your 0 to that point and work with that instead. That's roughly what you do. But these are just pre-processing steps. There's like some just bells and whistles that we need to add in order to manage things. But just the most interesting situation is when a polynomial already satisfies these three properties. Okay. Now, how did we proceed with the polynomial factorization? We began with a factorization of f of x comma 0. This is a univariate polynomial, and we've already seen how to factorize univariate polynomials over finite fields. So therefore, we said, okay, let's start with the factorization of f of x comma 0. And I am told that this is a square free polynomial. So if at all I factorize, it will factorize into a product of like distinct irreducible factors. So let's just take G0 to be one of them and H0 to be everything else. Okay, and furthermore, since I'm assuming that f is monic, all the factors will also be monic. So so you might as well assume that G0 is monic to begin with. Okay, of course, it may be possible that f of x comma 0 doesn't factor at all. Like it's already irreducible, but that is just an easy condition for you, because that automatically tells you that, well, in that case, the original polynomial itself should have been irreducible. Well, because if the original polynomial did have factors, substituting y equal to 0 in the factors will give me another factorization. So therefore, so if f happens to be irreducible, f of x comma 0 happens to be irreducible, I can safely output that f is irreducible. Okay, good. That was the base case. What do we do with the base case? We then do Hensel lifting by just interpreting the base case as a factorization modulo y. Okay, G0 and H0 were actually just polynomials in X, but I'll just pretend as if there are bivariate polynomials which just don't happen to use y. Okay, so I have some factorization that is modulo y with the property that that they are coprime, in the sense that there exists A and B such that AG0 plus BH0 is equal to 1 mod y, because that I can get from the fact that f of x comma 0 is square free. And I know that G0 is monic. So Hensel lifting tells us how we can compute these lifts of the current factorization while maintaining the fact that each of the lift is a sort of a refinement of what you started off with. Okay, that is G1 happens to be equal to G0 mod y. That is, you're only adding whatever multiples of y to G1 and so on, and you maintain monicness throughout. And Hensel lifting even tells us that such a lift is unique. I mean, there is only one possible lift that we might end up with. And we lift it until, our 2 power k becomes bigger than 2d squared. And as you can imagine, this 2d squared is coming from the fact that at some point a resultant will be involved, and that resultant will have a certain degree of 2d squared. So we're just making sure we are beyond that. Okay, so good. So that's what we did there. And then came this thing of, once I get a factor gk, that's not a reason for me to figure out that the polynomial is not irreducible or something, because we saw examples of it last time. Okay, so there is a recovery step that happens now where we need to figure out, does this gk correspond to an actual factor or not? Okay, and for that, we tried to solve this system of equations, where we basically wanted to know, are there non-zero solutions, g tilde and gk prime, that satisfy this equation such that g tilde looks like a reasonable factor for f, in the sense that its x degree and y degree are what you should expect from a factor of f. Okay, and gk is whatever is needed to make this equation satisfy. Okay, intuitively speaking, as we mentioned last time, whatever GK I have currently, if anything, it may be part of what is an actual factor of F. And we are trying to figure out what is this actual factor of F. And this system is a way of trying to get a handle on that. We are just saying, can I multiply something to my GK such that surprisingly, even though at this point, my Y degree could have been as large as Y power 2 power K. It could have been as large as 2 power K. But is there a way to multiply it with something such that the Y degree just crashes to something like this? Okay, so that's what we are trying to ask. And if there is no such solution, we will just return that the polynomial that we started off with was irreducible. Okay, but on the other hand, if there was some solution, we did get a non-zero G tilde, then it will turn out that the GCD of F and G tilde will always be non-trivial, and it will give us a factor. Okay, and that was the overall algorithm that we saw. So might be a good point to pause for questions if there was something that was unclear, and if I can just go over it before we try and see what are the modifications we may have to do for integer polynomials. Okay, okay, good. So it's the steps are quite simple. You start off with your base factorization, which is something like do whatever you can types. And then you keep trying to improve the situation to a high enough point. And then from your final state, which is some GK times HK, you try and see, am I being fooled into thinking there is a factorization when there is no factorization? And you solve this recovery step, which happens to be a system of, one second. Okay. So yeah, so this is what happens. Okay, good. So now let's proceed to factorizing integer polynomials, which I don't know, it's a fun task. So the integer polynomial is, as you would expect, it's given as a list of coefficients. I'm going to assume that D is the degree. Then I might make a mistake of thinking mentioning N for the degree instead of D, but you know what I mean here. Okay, so the first step we want to get a sense of is what should the running time be? Like what should we aim for? Now, previously, for all bivariate factorization or univariate factorization, etc., we were trying to get polynomial in D and log Q. That was the running time we were hoping to get. Okay, and why did we choose D and log Q? Because we were saying that, well, what is our input length? The input length was, I'm given a set of something like D plus 1 field elements. And each field element, it's some element of FQ. So it only takes log Q bits. So my input is of length D log Q. And I would like to run in polynomial time in the input length. Whereas here, you are dealing with an integer polynomial. So, the input length needs to be a little careful. I can't just say it is some degree D polynomial. I need to be a bit more precise about things. So here I just want to say that this is one time where coefficient sizes matter, because that's going to determine what our input is. Okay, so what we are going to do is we are going to assume, okay, that all these FIs are integers between, 2 power C and minus 2 power C. Okay, so that is requires C bits, or maybe plus 1 for the sign or whatever, but doesn't matter, like about C bits. Okay, so therefore, the input length, this is order C times D, because I have D coefficients, each of which take about C bits to represent. Okay, and therefore, what I'm interested in is I want poly in D comma C running, because that's polynomial in my input. Okay, this is what I should be willing to tolerate. Now, let's ask the first question, which is this even a reasonable ask? Okay, what are we asking? What is the task that is in front of us? I give you a polynomial f. I promise to you that, okay, I give you a polynomial where the coefficients are small. I mean, like it's within like c bits or something. And I want you to compute its factorization. Now, the first thing is, it's not clear on the face of it that, okay, maybe let's say g is a polynomial that divides f. What sort of bounds can you put on the coefficients of g? Like, is it even reasonable for me to say, write down what the factorization is, if the coefficients that g has are like completely ridiculous? Okay, so one of the things that we would want to know is just the following, because I am asking you to output an irreducible factor of g, sorry, of f. So the first thing that we might want to know is how large are the coefficients of g? If the coefficients of g is like bigger than this many bits already, then this is utterly hopeless. I mean, like, it seems like completely impossible to ask for us to output the factorization of f at all. Okay, so fortunately, there is this bound which is called Mignot's bound, okay, which says that, okay, if g is an integer factor, then you can give some bounds for g, which at least tells you that it's reasonable. I mean, the bound looks ugly. It looks like it's exponential, but notice that this is in terms of magnitudes. So I mean, I always find it convenient to just think of it as something like CD squared, just as a stupid bound, because this is 2 power CD, this is 2 power D log D, this is 2 power D. They're all smaller than this, so I can sort of absorb it into this. And this basically means this is CD squared bits each. So the bit complexity of the coefficients of the factors may be larger, but fortunately it's still manageable. My original input was of length CD. Now each of these are also of length something like CD squared or something, which is okay, which is something that is acceptable. Like, I can tolerate this thing. So at least Mignot's bound tell us that, so therefore, factorization in Zx is at least plausible. I mean, there's no flat out way of saying that, no, this is impossible to do. I mean, it says that, okay, the coefficients are not that bad. Okay, so let's see a proof of this. In some sense, things like this are, at some point it becomes standard, but it might be that, I'm just pulling a rabbit out of the hat sort of situation. But yeah, but at some point, all of these sort of arguments will become quite standard. So let's say f is equal to, let's give it some names. So let's say that this is AD x power t plus AT minus 1, whatever, x power t minus 1 plus blah, 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 till some a naught. I probably used f naught above. I don't know why I switched to a naught, whatever. Okay. Now suppose, okay, alpha is a complex number. You might be wondering, why am I going to complex numbers right now? Okay, but just bear with it for a minute or something. So, oh, by the way, so I want to be able to, the reason I'm going to write this is that I want to write this as AD into product of x minus alpha I, where I goes from, let's say, 1 through t. I mean, where these alpha i's now happen to be complex numbers, where these alpha i's are the roots of the polynomial, because we know that every polynomial has roots within the complex numbers. So these alpha i's are something. Okay. So let's first, okay, let's pick up any alpha that satisfies, okay, f of alpha is equal to 0. That is, it's one of those roots. Okay. Now I want to know, how large can this alpha be in terms of its magnitude? Okay. So I want to know how large is alpha. Okay, so what do I know? I know that AD times alpha power D, this equals minus of AD minus 1 alpha power D minus 1 plus blah, blah, blah. plus A naught. Okay, I'm not doing anything fancy here. So what I'm going to do is just apply a modulus operation on both sides. Just compute the length on both sides. So what do I get? I get this. Modulus of alpha par D is the same as modulus of alpha par D. Okay, and this thing just becomes, this just will sort of say that this is at most. In fact, it's exactly equal, because if the left hand side was equal to the right hand side, it better be the case that the lengths are the same. But I'll put an inequality because we're going to keep using triangle inequality at this point. So notice that this is something I can write as it's at most AD minus 1 plus AD minus 2 plus blah, 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 plus A naught times alpha par D minus 1. Okay, I'm just putting it with the largest possible thing. Okay, here I'm already assuming that the mod alpha is bigger than 1, because we are eventually trying to say that how large is alpha. I'm trying to give an upper bound on alpha. So if mod alpha is less than 1, then great. I mean, we already have an upper bound which is 1. Okay, so this is one expression that we have. And this, what is a stupid bound on this? I know each of these AIs is at most 2 power C. And I'm adding up B of them. Okay, so this basically will immediately tell us that mod alpha is at most D times 2 power C. Okay, because this guy is at least as large as mod alpha par D. And there is a mod alpha par D minus 1 on this side. So you cancel that off and you basically get. So it tells you that if there is a complex root, that complex root can't be too large. Okay, so good. Okay, now let's, okay, this is not what we wanted to do at all. We wanted to get a sense of what are the coefficients of G going to be. Okay, so now suppose G divides F. Okay, then what does G look like? So I know F looks like this, and G is a factor of that. So what should G look like? Well, notice that G has to be of the form some AD prime, where this AD prime possibly divides this AD. Okay, times some product of X minus alpha I, but now maybe this I comes from some smaller subset. Now some subset of roots may be a part of G, but some of them may not be parts of G. Okay, so what is okay? So let's forget this AD naught for now. I'm just going to assume that no, this is 1. I mean, it doesn't matter because that will only I'll just multiply eventually by 1 2 power C later on. So I'm just ignoring this for now. So suppose this G was just looking like this. Now, what can you say about what is G naught? What will this be equal to?
Sum of alpha in S.
No, G naught is the constant term.
Oh, G naught is the constant term. That's going to be a product.
Right. So this will be something. I mean, if you forget about the signs, etc. Okay. So this is basically going to be the product of all alpha I, where I belongs to the set S. So maybe I'll have to multiply by this. If this A naught exists, oops. So if this AD prime exists, then the AD prime will show up. But let's ignore that for now. Okay. What about G1? What is this going to be?
Like the sum of products taking.
Yeah. So
one less.
Right. So this is like, in some sense, sum of all D minus 1 or whatever, this DG minus 1 products of alpha I's. Okay. That is, this is the, you take all possible products of modest many of these roots and add them up, but there's only one of them. So you get a single product. Whereas this will correspond to, like for example, if the size of S was equal to 3, so which means there are 3 roots. So you get alpha 1, alpha 2 plus alpha 2, alpha 3 plus alpha 1, alpha 3. So you will take all possible, whatever, that minus 1 products. And these things have a name. So they are called elementary symmetric polynomials. In the alphas. Okay, so in general, if I look at what GI is, this is exactly going to be summation over all subsets of these roots such that the mod of t is equal to mod of s minus I. And you're just going to take the product of all I in t of alpha. Okay. Now let's come up with a stupid bound of how large can this be. Okay. How many summons do I have on the outside? Worst case, it is d factorial. Okay. D factorial is at most d power d. Okay. So I'm going to write this as d power d times. How large is each of them? Well, whatever is the bound that we got for alpha, that raised to the power d. Okay. And the bound of alpha, we just calculated that this is d times 2 power c, the whole power d. It's a stupid bound, but at this moment, we are completely fine with it. We are just trying to convince ourselves that this is reasonable. That's it. Okay. So if you just notice that this is going to basically become, what is this? This is 2 power d log d plus another d log d plus cd. And it's convenient to just bound this by 2 power cd squared or something. I mean, assuming d is large enough. And so because cd squared clearly dominates everything that's there on top. And yeah, and that's Mignot's bound. It's a very simple argument. And it basically is to convince you that computing factors of f is reasonable. I mean, it's not completely crazy to ask for an algorithm for computing the factorization of f. Okay, are there any questions? I mean, was there something here which was unclear? Okay, great. So now let's move to beginning to compute a factorization of Zx. Okay. When we were doing bivariate factorization, we made some simplifying assumptions. Like, let's assume it is square free, let's assume it is monic, whatever nice structure you want to assume. Okay, let's say you assume all of those structures. I tell you it is monic, I tell you it is square free. Okay. And then the next question that you get stuck with is like, okay, now what? Okay. Now let's go back to our bivariate factorization and ask, what is the base case that we did? We basically said, what are the factorizations that I know at that point? And let's somehow do the thing that we know. Okay. Now, if you wanted to do something similar here, what would that be?
Like,
okay.
We know some one thing we know that, I mean, there's some bound we have distributed C or something on the coefficient.
Okay. Yeah.
Is there some way to sort of import the finite field thing here, like univariate factorization?
So you're almost there. So okay. Let me try and give you a hint to sort of say, what should our y be here? So what did we do in the bivariate factorization? We basically said, let's set y equal to 0 and then work with that. Okay, but why did we do that? The reason we did that was because we were like, look, I don't know how to factor bivariate polynomials, but I do know how to factor univariate polynomials. So let's do that instead. Okay. So suppose you were to take the similar view and say that I don't know how to factor into polynomials over integers, but can I sort of, make some, I mean, last time we basically said, instead of factoring f of x comma y, we instead factored f of x comma y mod y. That was like setting y to equal to 0. So what should we do instead? So what are the factorizations that we know? I mean, at this point, so far we have only been dealing with factoring polynomials over finite fields and stuff. Okay, can I convert f to a polynomial over a finite field and then hope to factor that instead? Don't know if you people are like overthinking this thing. I mean, it's just a completely silly thing to do, and it'll.
The coefficients are bounded for the method.
Asif, I couldn't hear you. Can you be a little louder?
Sorry. Coefficients of f and the factor that could be possible are bounded by this.
Yeah, it's bounded by some bound, whatever Mignot's bound gave us.
So we can work in a finite field of big enough order.
Good. So in fact, at this point, let's not even try to choose a prime. I mean, let's choose a finite field that is large enough for something. Let's just do something utterly simple. We'll pick a prime P, whatever P we want. Okay. But maybe there'll be a later point where, as you said, it might be useful to choose a prime that is large enough for whatever. But at this point, I'm just going to just go modulo, I don't know, let's say my favorite prime is 13. I just go modulo 13. Okay, I just interpret this polynomial as a polynomial over the field F30. Okay, so in some sense, so this Y will be a prime P. Exactly what prime it is, we might come to it a little later. But yeah, you're right that it makes sense to choose a prime P depending on what sort of coefficients we have in mind or something. But what we are basically going to do is just choose a prime P to play the role of Y. Okay, so I'm just going to compute what f of x mod P is. F of x mod P is a polynomial. So basically what we are saying here is that f of x mod P, this I can think of as a polynomial in fpx. By mod P, I just mean take every coefficient, just reduce it modulo the prime number P. Okay, so now I get some polynomial which is over a finite field. And let's try to factor it. Okay, and again, hope to improve it because we are again taking the view that that's the only thing I know what to do. So let's do that and let's slowly improve it so that we deal with, we'll eventually figure out how to recover and stuff. Okay. So now let's maybe make a little bit of, spend a little bit of time of what should our P satisfy. Okay. Now, the first thing I would need is that often it's convenient for polynomials to be monic because then we can deal with these things properly. If you want, you might as well assume that your original polynomial was monic to begin with. Then this problem doesn't arise at all. No matter what you go mod, the leading coefficient is still going to stay 1. So you needn't have worried. Otherwise, what you would have done is you just need to choose a prime that does not divide your leading coefficient. Because then it will be a unit and you sort of divide off by whatever is necessary or something. Right? So that's one thing you can do. So therefore, so here we may want P to not divide whatever is the leading coefficient. Okay, so that's step 1. And earlier we also wanted f of x comma 0 to be square free. The analogous thing here is going to be I want f mod P to also be square free. Okay, what should this? So how do we ensure that this is true? So firstly, we can assume that f is square free because we can sort of take its GCD with its derivative or something like that. But it may be possible that f is square free, but f mod P is not square free. Right? But when can that happen?
I mean, if different factors look the same mod P.
That's right. So, okay, but again, you have a concrete object that you can relate this thing to. F being square free means that the resultant of f and its derivative was non-zero. Now it means it is non-zero as an integer. Now, if I want f mod P to also be square free, what should P satisfy? or rather, what is a bad choice for P? Like what sort of P's will result in something being F is originally square free, but F mod P is not square free? Feel like I'm maybe losing a few people. So what does it mean to say F is square free? This implies that the resultant with respect to X of F and the partial derivative of F, this is not equal to 0. Now, what does it mean to say that F mod P is square free? So the resultant of F mod P with the derivative of F mod P is going to be equal to 0. I want that to be like not equal to 0. But how is the resultant of this and the resultant of F mod P related? You are literally looking at the entries of the matrix, and entry wise, you are just going mod P. Right? So the only way this can happen is if the prime P happens to divide this non-zero integer. So therefore, what we want is I don't want P to divide the resultant of F and the derivative of F. Okay, so you will need to choose a prime such that like the above two conditions hold. And we will just try out a few primes and make sure that this works. Okay, so this is like again, it's one of those pre-processing steps that you need to do. But at this point, we might as well just assume that we have a prime P. And now we will apply our finite field factorization algorithm. We'll apply the Cantor-Sassenhaus algorithm and get some factorization that looks like G naught times H naught, where G naught is monic and irreducible over FP. Okay, and H naught is whatever was the rest of the factors. Okay, the next step we are going to do is do the same thing we know how to do. Okay, we'll start with this factorization and lift it. Now you won't get mod P, you will now end up with mod P par 2 par K. I mean, P is literally just playing the same role that Y was playing in the bivariate setting. And we'll again do this for large enough. We know somewhere down the line, some resultant is going to show up. We don't exactly know what this K is supposed to be, but let's keep this floating for now. We'll figure out what the right value of K is. Okay. And then comes the part which is unclear what to do, which is from this GK, I want to recover some G tilde or return irreducible. At this point, I have no idea of how to do this. Like, what does that mean? And then we're going to say, if we didn't find a G tilde, we will return irreducible. If we did find a G tilde, we'll return the GC. So this is the algorithm. Okay. It's just that we need to fill in the blanks or rather we need to replace these red steps with suitable analogs once we realize exactly what we need. Okay, so I hope the overall structure is clear. We just find a prime P which is reasonable so that I can start off with a situation of this sort. Okay, and then you proceed. And the key part is it's unclear exactly what this recovery is going to do. Okay, so let's just write down the recovery step and see what we need to do. What was the recovery step in the bivariate setting? And if I wanted to do the recovery step in the ZX setting, what do I end up? What was the rough intuition? This GK, whatever we have lifted till now, is part of a factor. It's part of an actual factor. We are trying to figure out if such an actual factor exists or not. And what did we do? We basically said, can I multiply GK with something such that when I go mod Y par 2 par K, magically the product is very reasonable. It's looking very reasonable in the sense that its X degree is what you expect from a factor and its Y degree is what you expect from a factor. Okay. Now, what is the analogous thing that you need to do? I want to solve for G tilde of X and G prime of X such that if I multiply GK with this GK prime and go mod P par 2 par K, I want to say that G tilde looks reasonable. Now, one thing is that I can always say that the degree of G tilde must be smaller than the degree of F. That is okay. But what is unclear is what is the analog of this in this world? What does it mean to say that the degree of Y is small? What is the degree of P here? Okay, so I mean, let's go back to the sort of examples that we saw when we did this bivariate lifting. We lifted and we got a GK that looks utterly unreasonable. I mean, the degrees in Y's were enormous, the degree in X was enormous, but they were all coupled with some multiple of Y power 2 power K or some such nonsense like that. Okay, it was just a massive, I mean, really ugly expression. But somehow when we multiplied it with the right thing, the product that we got looked so reasonable. I mean, it really looked like a factor in the sense that no, the X degree was small and the Y degree was small. Now, what do you think will happen if you did the same thing mod P power 2 power K? Okay, again, you will get some horrendous X degree. There'll be all sorts of crazy things that will happen here, but they will all be multiplied with numbers that are divisible by a very, very large power of P, because P is playing the role of Y, such that when I multiply them together, somehow something happens. Like if you're willing to ignore large powers of the prime P, suddenly things drop substantially. Okay, so the point is, the thing that I'm trying to get to was that in the bivariate case, the reasonable, whatever we were calling as reasonable for G, was that its X degree must be at most the degree of F and Y degree must be at most the degree of F. What is reasonable here?
The Mignard bound?
Exactly. Okay. And I want to say that the coefficients of G tilde are small. That is, it's like within what you expect in the Mignard bound. Okay, so it's a very similar setup, except it's of a slightly different nature. Okay, it's something to do with bounds on each of those, whatever coefficient that you see. And there is one extra hurdle also. I'm really interested in integer solutions, because we're finally coming up with integer polynomials and so on. So therefore, the fact that we are working in the integer world will sort of slightly change things, because this was a system of linear equations over a field. Whereas here it's a system of integer equations, so the game is slightly different. Okay, so let's just write down what sort of systems do we end up with. Okay, so I have an expression of this sort which I'm trying to solve. Okay, so so this is the expression I'm solving for. The green colored things are what are the unknowns. In fact, I literally only care about the G tildes. This is just something to sort of say there exists some G case that happens. Or something. What I'm really interested in, is there a G tilde with small coefficients that you can get here? So let's write this down differently. Okay, so I mean, I want to know. Okay, so I'm going to write this. Okay, let me just write down an expression and then you tell me if this is sort of not making sense or something. 0 of, what should I put here? I should put GK0, GK1, GKB minus 1. Okay, so this is the constant term GK, I mean GK prime 0 times this polynomial. I have just written this as a vector. Okay, plus G prime K comma 1 of this matrix 0, GK0, P minus 2. So this is the, I mean, the linear part multiplied with whatever this is. And I'm just writing it down as a vector. Okay, this probably has to be a little larger or something. I mean, maybe it's not this length, but it's a little longer or whatever. Plus blah, 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 blah. I mean, so So maybe there's a whole bunch of zeros to begin with here. And maybe this is one extra thing that you have, and each of them, and you keep repeating this to sort of, I mean, I'm just going to assume that this D is the largest possible degree that you end up having. And this is going to be GK prime, whatever was this degree D is, times 0, 0, and then whatever. I mean, I'm not writing it in, I'm making a fool of myself here. So basically what I'm saying is I'm just taking this right-hand side. Okay, so this right-hand side is going to basically be some polynomial expression of total length being the total degree on the right-hand side, or that plus 1 or something. And I'm just writing this as some integer times a certain vector plus some other integer times a certain vector, etc., as some certain vector. Okay, and I want to know this is currently a vector that is made up of integers. If I reduce everything mod p power 2 power k, do I end up with something that looks, how do I put it? Do I end up with something that looks small in all the coordinates? And by small, what we mean is like within the mignon bound. Okay, there is this annoying mod p power 2 power k business, but that also we can absorb to sort of say this plus a0 into p power 2 power k 0, 0 plus a1 into 0 p power 2 power k 0, 0 blah 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 till a whatever 0 p power 2 power k. Okay, because going modulo p power 2 power k is just adding and subtracting multiples of p power 2 power k in each coordinate, and I'm writing it in this form. Okay, maybe I should have converted all of these to black. Okay, so okay, so what we are asking for is, are there integers, whatever are the green things, such that the resulting vector somehow happens to have very small coordinates? Again, by very small is like within the mignon bound. Okay, so another way of saying this is I give you a bunch of vectors and I ask you, is there an integer combination of these vectors that is short in terms of its length? Okay, and this is where it naturally leads to studying what are called lattices. Because lattices, basically, the definition of a lattice is it's all integer linear combinations of a certain generating set. Okay, and specifically what we are interested in is we want to know what are short vectors in a lattice. That's what we are trying to compute. So if we write down our recovery system and you really ask what is this recovery system trying to do? Given a GK, which was what we got from the lift, there will be a specific lattice that involves this GK. And we are really interested in, is there a G tilde in this lattice that happens to be short? Okay, so that's what we are really interested in. Okay, good. And so that's going to be our segue into this new thing, which is called a lattice. And let me just define what a lattice is. So given a bunch of vectors that are made up of integer coordinates, the lattice generated by them is basically the set of all integer linear combinations of them. So sometimes we might refer to it as just L of B1 through Bm, or maybe you use this ideal notation with the subscript of Z to just indicate that you're not looking at all possible combinations of them, you're looking only at integer combinations of them. Okay, and this is what a lattice is. Okay, and the canonical example of a lattice is the integer lattice, which is if you take your elementary vectors and then sort of look at all integer linear combinations, I mean, you will end up with this. Okay, so this is basically what the integer lattice will look like. So you only have these integer points or whatever, and so that's what the integer lattice is. Okay. Now, good. So what is the shortest vector problem, or the SVP? It's an extremely important problem in a whole variety of fields, and it's actually taken the current, almost the entirety of crypto. It's just taken by storm. I mean, like so much applications of the shortest vector problem and related problems in crypto. Okay, and the problem is what is stated here, which is that I give you a basis. Okay, I give you m vectors which are all in some n space, and I ask you, can you tell me what is the shortest vector in the lattice? Or I additionally give you another parameter k, and I ask you, is there a vector of length smaller than k in your lattice? Of course, other than the zero vector. Okay, and this is called the shortest vector problem. And like almost all interesting problems, it turns out that SVP is NP hard. Okay, so we somehow happily reduced the problem that we were hoping to solve to this question of finding short vectors inside a lattice. Okay, and then we said, okay, fine, if only we can solve the shortest vector problem inside an arbitrary lattice, we would be sort of done. And then we realized that, oh damn, so the shortest vector problem inside a lattice is actually NP hard. Okay, and does someone have a guess on how do we go about fixing this? Okay, now that we know it is NP hard, what do we do?
No, so this is NP hard, like when you're working over what?
So I'm somehow not able to hear you that.
So you meant like for general lattices, this is NP hard.
That's right. That's right.
What about just like integers?
No. All of these are integer lattices. I mean, they're all, the basis vectors are all made up of some integer coordinates. And finding the shortest vector is turning out to be NP hard.
I mean, maybe you don't want some shortest, something
Excellent.
short enough.
So we don't need this. What I want is I want to find short vectors. Okay, I'm okay with some slack. I'm not particularly going to be so sort of tied up to the fact that I want the smallest solution that is present there. I just want a short enough vector. Okay, and fortunately, there's this beautiful result of Lenstra, and Lovash, which is often called the LLL algorithm. There are there's another LLL, of course, that also involves Lovash, which is the Lovash local lemma. This is not that. This is a different LLL. And this LLL, this is the same paper that also proves the factorization over Z. So the LLL algorithm as a subroutine has the theorem that I have written down, and it uses it to solve the problem we are trying to solve, the integer factorization problem. And here is what LLL says. It says that there is actually a polynomial time algorithm which will give you a short enough vector, in the sense that you may be away from the optimal by a factor of about 2 power n by 2, where n is your ambient dimension. Okay, so this is what LLL says. I may not be able to find the shortest vector in the lattice, but I will be able to find some vector b that is in the lattice, which is not too long. Okay, and what we will do in the remaining about 20-25 minutes that we have is to just complete the factorization algorithm assuming error.
So in our case, like the n is just that d or something. Right?
Yeah, it's basically the degree of whatever this gk is going to be. Yeah, and that will be d. Yeah. So if we start off, I mean, it's something that I sort of, I didn't go into too much details, is that notice that G0 to begin with will have at most d coordinates. And every time in the Hensel lift, I might be adding things, but you need to convince yourself that the degree doesn't grow up too much when you do the Hensel lifting process or something. But it's something that is quite manageable. So the n will, the n that we'll be using for in the LLL algorithm will basically be the degree of the polynomials involved. Okay, so is the problem statement as the setup to lattices clear? So this is the only thing I'm going to talk about lattices in today's lecture. And then the next lecture, it will be completely about lattices because we are going to try and prove the LLL theorem. Okay, but for now, we are going to assume this theorem and just proceed with the factorization algorithm and see how there were some missing parts in the factorization algorithm. We can now instantiate it to whatever we want. Okay. Okay, good. So here is what has happened so far. If we go back to our factorization algorithm, we picked a prime P, and this P was such that your initial whatever nice conditions satisfied. Okay, and then we kept lifting it until a certain point. So what is unclear is like, what is this certain point is unclear, and we have to figure that out now. Okay, so what we want to do is now the new thing is going to be the recovery step is going to be to try and find the short G tilde in this system. And this will basically become a lattice, and then you'll basically say find a short enough G tilde in the lattice, and we will use the above LLL algorithm to do that. Okay, and suppose we are expecting a G tilde that looks a certain way. That is, we are expecting a G tilde that is within the Mignard bound or whatever. But LLL is going to give us a short solution in the lattice. It is going to return something. And if the G tilde that LLL returns is completely unreasonable, in the sense that the sizes are so high that there is no way this looks like one of the solutions I'm looking for, we will just return irreducible. So this is a blank we need to fill in. We need to figure out what should go into this blank. So that's step one. Otherwise, we somehow want to guarantee that whatever G tilde we have obtained, it will have a non-trivial GCD with F. Okay, so that's how the rest of it is going to proceed. So we really need to figure out what should this K be and what should this blank be. Okay, and why is it the case that this GCD will always return something non-trivial? Now, if we did manage to find a short enough vector, similar to what happened in the bivariate case, we wanted to say that if F was reducible, there is always a solution with the constraints we put in, and any such solution gave us a factor. And we want to do something similar. The constraint we are putting in is we are looking for a vector that is smaller than a certain threshold. And I want to say if F was reducible, there must be a G tilde that is short enough. And any such G tilde will give us a factor that we want. Okay, so we need to get a sense of, what should this K be? Okay, so what do we know? The same intuition from last time. At this point, we have some GK. Okay, so we know that at whatever GK we have is sort of part of a true factor G star. Okay, and how long this G star really? And this is where, as Varun pointed out, this is just going to be whatever Mignard's bound gives us. So Mignard's bound basically says that each coordinate is at most 2 power CD squared or something. So Mignard's bound basically says that this D star is at most 2 power CD squared. Maybe there is an extra factor of D because there are D coordinates, depends on how you are talking about length. Like, is it L2 norm, is it L infinity norm, etc., etc. But these are details that we won't really, it won't matter to us at all. Okay, the coordinates are the ones that are long, that are really, really large. The number of coordinates is like completely negligible. It's just D. And we are dealing with each coordinate being like 2 power D squared or something. So Mignard bound basically tells us that there are about 2 power D squared. The right G star is expected to have length about 2 power D squared. Okay, so of course, this basically tells us that the smallest G star in the lattice is no longer than 2 power CD squared. Because such a G star will be a solution, just like we had it in the bivariate setting. But of course, it may not be the smallest vector, but for all we know, maybe that is the smallest vector. But LLL is not expected to give us the smallest vector. It will give us a small enough vector. So therefore, LLL will return, or rather, LLL ought to return some G tilde of length at most. What is this going to be? This is going to be 2 power CD squared times 2 power D. Okay, I am just going to absorb all of this and be sloppy and just say this is at most 2 power 2cd squared. Okay. So the first blank is if this is bigger than 2 powers, 2cd squared, I'm just going to say it is irreducible. Because I know if f were reducible, I know there must have been a short vector of length at most 2 power cd squared, which means since LLL makes only an additional factor of 2 power d in the length, I must have gotten some vector of this much. But on the other hand, if LLL gave me some completely ridiculous vector, like the length is too high, you just immediately say, no, it is irreducible. So this is not the sort of vector I'm looking for. Okay. Suppose that doesn't happen. I want to claim that the GCD is always non-trivial. Okay. Now let's come to the last part, which is why are we sure that suppose we did find a G tilde whose length was only this much, 2 power 2cd squared or something. How are we sure that GCD of f and G tilde is always going to be non-trivial? So how would you go about trying to solve this? So what's the one thing that you do when you want to somehow show that the GCD between two things is non-trivial?
Resultant.
Yeah, exactly. So let's just look at the resultant. So let's look at the resultant of whatever, our polynomial f and whatever was G tilde. G tilde is what we got from the LLL. Okay, good. And so I'm hoping to show that this is equal to 0. But like last time, we know that this is equal to a times f plus b times G tilde. Because the resultant is always can be written in terms of f and g, some polynomial combination of f and g. Okay. Now let's just go modulo p power 2 power k, because we have expressions for both f and G tilde in terms of mod p power 2 power k. So this is going to become a times gk times hk plus b times gk times gk prime mod p power 2 power k. Okay, and like last time, we're going to write this as gk into a times hk plus b times gk prime mod p power 2 power k. And now what do we do? So what is the left hand side? Like where does that, like what sort of an element is that? So f and g were both univariate polynomials. So what will the resultant of f and G tilde be? What sort of a number? Is it a polynomial? Is it
number?
Right? This is just an element of z, because it's a determinant of a bunch of coefficients of f and G tilde. They're all integers. So when I take that thing, I'm going to get an integer. But on the other hand, what do I know about gk? This is monic in x. So once again, you have this thing of the left hand side is supposed to be an integer, but apparently it is equal to a monic polynomial times another polynomial. Now, how the hell can that be possible? So the only multiple of this monic polynomial gk that happens to be an integer is the polynomial 0. Okay, so this basically tells us that the resultant of f and G tilde, this is equal to 0 mod p power 2 power k. Okay. Now I want to get the same statement without the mod. And once again, we have not yet used the fact that k was larger than something. Okay. So if k was, so now what do you want to choose k to be? so that this equation will guarantee the same equation without the bound. So the left-hand side is some integer. And right now, the only thing I know is that it is an integer divisible by p power 2 per k.
How large
Excellent.
would the resultant be?
So how large is this guy? I mean, as an integer, how big is it? Okay, let's just write down that matrix. So it will be made up of a bunch of f's and then a bunch of this g tildes. Okay, how large is this matrix? It's some 2D cross 2D matrix. What sort of bound can I put on every entry? Well, LLL was telling me that, the bound is at most like 2 power 2 CD squared. That's the bound on every coefficient here. So worst case, let's just assume it's a 2D cross 2D matrix where every number in this matrix is at most 2 power 2 CD squared. Okay, so therefore, if I look at the determinant of this is at most something like 2D factorial times 2 power 2 CD squared whole power 2D. Again, stupid bound, I don't care. Okay, and if p power 2 power k is bigger than this quantity, then we are done. Right? Because now it will tell you, you're basically saying that this as an integer is something. And when I go mod a much, much larger thing, apparently it is 0. So it better be the case that was 0 to begin. I mean, previously we had done this with respect to the degree in y. And now we are doing it just based on the magnitude of the sort of things that we are dealing with. And that's it. And that completes the proof of the univariate factorization algorithm. I mean, it's a beautiful thing. I mean, it's just that, it's once you have the bivariate factorization, if you set it up the right way, the recovery step just becomes a lattice question. And it's easy to have just said, oh, no, finding short vectors in lattice is like NP hard, let's not even go there. But the point is, no, you don't need the shortest vector. You just need a short enough vector. And a short enough vector is something that is provided to us by the Lenstra-Lovász algorithm. I mean, which is also an absolutely beautiful algorithm, which we will see in the next lecture. Okay, so, and we just used that and just adapted our bivariate factorization in order to get our thing. I mean, the rest of the template is very similar. It's just that every once in a while you have to just make sure that you're looking at the right generalization that you want. Okay, and and that basically completes the univariate factorization proof modulo the LLL algorithm. And in the next class, what we are basically going to be doing is we're going to spend some time looking at lattices and the LLL algorithm. Okay, and it's a pretty remarkable algorithm that we'll see in the next class. But since I have some time, I'll tell you a little bit about the fact that, maybe this is something that is maybe a little on the mathematical side of things and less on the computational part. So there is this amazing similarity between these two rings, FPX, what did I do? Yeah, so these two, ZX and Y. In some sense, I just want to sort of say that, this has two separate things that we can use, like two variables, something that's playing the role of two separate variables, like there is X and Y, and that somehow P and X appear to play the role of X and Y in this other thing. And so these are both called dimension 2 rings. Okay, there is a notion of what is called dimension, and under that dimension, surprisingly, ZX actually has dimension 2 and not 1. And so there is a deeper reason as to why factorization in ZX somehow mirrors a lot of factorization in fp x comma y. Okay, and I mean, and if this is something that people are familiar with, maybe because of some other context, I mean, though I'd be curious about how you came across the notion of dimension of rings and so on. It's just that it's a very, once you have that perspective, it's very natural to just imagine that P is going to play the role of Y. Okay, and the notion of degree, which is like, a degree, you can just think of it as saying that what is the largest power of Y that that you are willing to exclude. That's basically the same thing you are doing when you are going mod p power 2 power k also. There also you're basically saying what is the largest power of p that you're willing to exclude. So it's just that you are doing the bivariate factorization over some other dimension 2 ring, where your notion of length, which used to be degree, has now been replaced by L2 norms and stuff like that. Okay, so it's okay. It's just a high level thing of as to, in case people are wondering why the hell does it mirror the bivariate factorization more than the univariate factorization? Well, this is one underlying reason for this. Okay, so let me just stop here. I mean, like, we are ending a little early, but I think it's fine. I mean, this is a good point to stop. And in the next lecture, what we're going to do is do lattices and LLM. Varun, did you have a question?
Yeah. What is this like dimension notion?
So there is a, okay, again, but if people, I mean, like, this is all just optional parts of this lecture because we have to. So there is a notion of what is called a prime ideal. Okay, so prime ideal is an ideal which is a subset of R with a property that looks like a prime number. Okay, that is, I want to say, if a product AB belongs to this ideal, mentally tell yourself, if a product AB is divisible by a prime P, then you would want to say either A is divisible by P or B is divisible by P. Okay, so this implies that either A is an I or B is an I. An ideal that satisfies this property is called a prime ideal. Okay, so here are some examples. I mean, the ideal generated by X in, let's say, a univariate polynomial ring or something, or an ideal generated by primes inside the field Z, sorry, inside the ring Z. And this is also a prime ideal. This is in Fp of X comma Y. Okay, and so is this. These are basically all polynomials such that either the coefficient is an even number or it has no constant. I mean, the only constant term, I want the constant term to be divisible by 2. So this is one prime ideal. So the dimension term, there is a notion of dimension which corresponds to what sort of chain of prime ideals do you find in your ring. Okay, so there is a prime ideal chain which is 0, which is contained in the ideal X, which is contained in the ideal X comma Y, which is contained in the final ring. Okay, similarly, integers also have the same thing, where except you start with P, and then you look at 2 comma P, and then you look at Z X. So the length of the longest chain of prime ideals has a notion, that's what is defined as the dimension of the ring that you have. And turns out both of these rings have the same dimension because it has the same length of the prime. And okay, it's probably not helpful for people who have not seen this.
Is just, I mean, I don't know what this is, but is that 2 comma P you meant, or like X and X comma P? Or?
Sorry. I mean, I should have, I must have meant, I mean, this is P comma X. Okay, and take any prime P.
One thing below in that chain is X or P?
I mean, you can take whatever you want. They actually contain both.
Okay.
But maybe, I mean, just to have the same sort of correspondence, I mean, maybe I should probably call it X and P, so that you sort of literally see that Y is playing the role of P here. And yeah, and everything is happening just, like you just change y to a p, and then your notion of degree is being changed to L2 norms. The degree in y is getting replaced by something to do with coefficient sizes. That's it. Yeah, and this in general is called the Krull dimension. I mean, none of this is needed for you to really understand the univariate factorization algorithm, but it's just to say that there are some deeper reasons as to why it mirrors it so well.
Means whatever prime ideal we can take, we always get a chain of length 2 in this thing.
The only thing is, if you start off with this prime ideal, well, you don't have a choice but to just go to the entire thing. But in some sense, this is not the smallest prime ideal that you take. So yeah, so here, right now here there are like, I've just given you one chain of length 2. It turns out the largest possible chain is of length 2.
Oh, okay. Yeah.
Okay, and the largest possible chain is what is called the Krull dimension. Like it's a question of how many, what is your stack of prime ideals that you have inside your ring. And in some sense, every such new addition is behaving like a new variable. That's the rough intuition. So, and that's sort of why when we did the biofactorization algorithm, somehow y was playing the role of what, or rather the prime p was playing the role of what y was in the bivariate setup. Yeah, and okay, so let me stop here, and in the next, by the way, so there's a mild possibility that I might cancel Thursday's lecture and instead meet later, because our interviews and like PhD interviews are going to happen this week. But there seems to be some substitute, so I might still have it. But if it so happens that I have to cancel it, I'll just send a message on Acadly to let you know that we won't meet on Thursday, but we'll instead meet. I'll let you know when we meet next. Okay, so let me stop here, and we can. I mean, I'll sync with you guys on Acadly to let you know when we are meeting next.